Alright, welcome to another YouTube video. This one is on how to model a collar that is sandwiched between two springs on either side, and it has a pendulum coming down from it. The Matlab model is the one on the left here. I did it through deriving Lagrangian equations of motion and then simulating through ODE 45 and animating. And the one on the right here, I did it through sim mechanics, and I'll show both of those processes in this tutorial. So stay tuned, and if you enjoy it, please like and subscribe. Okay, so before we start solving in Simulink and Matlab, we want to just have a look at our figure and define all the parameters and variables. Parameters being the things that are constant, such as spring constant 100 Newton per meter for each spring, the length of the pendulum being 1 meter, the mass of the pendulum and the collar being 1 and 2 kilograms respectively. And now we look at the generalized coordinates, x being the distance of the collar from this vertical, and theta being the angle of the collar from the vertical. And at an initial position, I just randomly chose 0.25 meters away, and theta equals 45 degrees to give this thing some, initial values, and then we release it from rest. So x dot, or the velocity of the collar, is 0 at the initial time, and theta dot, which being the angular velocity of the pendulum, is also 0. Then to do it in sim mechanics, basically you need to create brick solids for each component and connect them through each necessary joint, which I'll show you how to do that. And then collect data such as velocity, angular velocity, position, angular position, etc. And then next I'll do it in Matlab by deriving the Lagrangian equation of motion, where this is T and this is V, T being kinetic and V being potential energy, and the Q is the generalized coordinate. So there's two generalized coordinates, so there will be two equations of motion, and there will be second order derivatives of the generalized coordinate. So we're going to see x double dot and theta double dot. We're going to have two equations with, it's going to be a set of two ordinary differential equations of second order to, describe it properly. And then we'll solve those equations using ODE 45, and then we'll use the results to animate and generate some plots. So let's start solving this. Okay, so we'll first start with Simulink. Basically, when you start up Simulink, you'll have this world frame or world configuration and a few other commonly used parts. And now we'll start by making the bricks. So we'll call a brick solid. This will be our base plate. Let's make it bigger. So from the top view, we can imagine now that we need to make the x dimension 2.4 meters, because that's the dimension where the collar will slide back and forth, and it'll be sandwiched between the two springs in that dimension. So the y dimension doesn't matter, we can make it 0.3, and the z dimension we'll make it exactly 0.1 to match the height and width and length of the collar. The collar is going to be a perfect cube. So apply F5. And let's choose inertia, point mass, make it something really heavy since it doesn't matter. 1000 kilograms. F5. Let's pick a color just to make it aesthetically pleasing. That green looks okay. Pick F5. Okay, now time to create our frames. So here's the XY. There's going to be a frame here on the left, and a frame on the right, and a frame right in the middle. So the frame on the left, get it by selecting this edge, use selected feature, and we'll name it left. Save F5. There it is. Now we'll create one in the middle. Selecting that face, use selected feature, call it color, save F5. Oops, shift and middle mouse button will pan. And now we select this last edge for the right based on geometric feature. Select right, save, apply and F5, and select OK. So here's our frames. So it came in nicely. The left one's on the left and the right one's on the right. So now let's connect this to the ground here. And we can run it to see what it looks like now. Should just be a flat plate. And there it is. It's just a flat plate. Okay, let's show the name of this. And we'll name it base plate. Base plate. Okay, we can either call another brick solid or just copy this one. We'll copy this one, but we'll change the dimensions and everything else. So it's gonna be a stop on the right side. Let's look at it from the top view. So the stop, we'll make it 0.1 on the X. 0.1 also in the Y. So it comes to the center. We can make it 0.1, 0.1, 0.1. Make it a cube. Select apply and F5. So now we need a frame here on this back edge to connect with the frame here. So once I connect them, you'll see what I mean. Let's remove all of these frames so we can just create new ones. And we will not need the middle frame for this part. Okay, actually, let me make it 0.2 in the Y. 0.2 in the Y, yeah, 0.2. Apply F5. Yeah, it'll make it taller. Okay. That'll help us with the distinguishing a little bit. So we need to here use selected feature. Call it right. Yeah, right is fine. Save F5. Another frame here. We'll call it left spring. Save. Apply F5. And now let's connect this one. Okay, this one we can rotate it just so we can imagine it. Control R will rotate. And now we connect these two together. Okay, now we need the same thing. Let's call this the right spring stop. Okay, now here, let's call this left spring stop. And we'll have to change these a little bit. Again, a top view will help us imagine it better. And we'll rotate with the middle mouse button and show the frames. Now we need this one to be on the back edge, so we can just modify it, edit it. We'll name it left. Select this, use selected feature, save, apply. And we'll need this here in the front. Selected feature, give an OK. Plot. Okay. I probably should have named this the right spring. That's okay. We'll rename it now. Okay, let's move these away from each other a little bit. There we go. And let's flip this with a Control R. Let's call this left spring stop and right spring stop. And rename this frame from left spring to right spring. Right spring. F5. Apply. Okay. Now we connect this to the left frame and run that, see what it looks like. Now we take a look at the top view, and it looks okay so far. Just a plate with two stops on either end. Now we're going to put a collar in the middle. Where do you go? Okay, here they are. Okay, collar, we need to just copy it again, copy another part, and the collar we said is 0.1 by 0.1 by 0.1. Alright, okay. Let's rename that to collar. Let's move this, delete this, and we'll delete those. Okay, now we need to define some frames. Let's see how these are. Okay, let's delete them all. We'll definitely need the R frame because that's going to connect to the pendulum. So let's take a top view. So we need here on this face a right spring and on the other face a left spring. And on the bottom we will need a, this is the bottom. We'll need another frame to connect to the base plate. Right, right spring. Save F5, F5. Oh, doesn't look right, does it? No. Okay, let's try it again. We just need it here on this face. Spring. Apply F5. Okay, that looks better. And now another one here on the left side. We're going to call it left spring. Save. Apply F5. Okay, then we need one on the bottom. So again, a top view will help us visualize it. It's going to be sliding in this X direction, so we need it here on this face. Bottom. Save. Okay, I'll call this bottom. I hit OK. Okay, now we need to connect the collar. The collar is connected through a prismatic joint to the base plate, and the base plate here collar, the bottom. So we cannot connect them directly because it's going to slide. So let's first create a prismatic joint. Okay, now if we read about the prismatic joint, it basically allows translation along the base z-axis while the base and follower axes remain aligned. So we need to translate that, but let's connect it and see so we can understand exactly what's happening here. So if we connect it and now simulate it, we need a top view. I think it's sliding away in the z-axis because of gravity. Yes, exactly. See, so it slides away. The collar slides away in the z-axis due to gravity, and it's in the negative z-axis. So it's this way. As time progresses, it is going through accelerating due to gravity in the negative z direction. So we need to change that too. So let's change that. Well, let's put our transform here. So we need a transform that's going to transform it from z to x. So z to x. And negative x to negative z. I'll put that here. This is our rigid transform. We need to place one on either side of this prismatic joint. So put one here. And put one here. So now, if we run it, we still have the acceleration due to gravity, but it won't slide anymore. because now it's in the x direction. We've translated to the x direction. But what we can do as a test is change gravity to be in the x direction, and we'll see it slide in the x direction. So let's do that. Okay, let's change the colors of these a little bit so they'll look a little bit better. Okay, let's make our stops red. Let's make this stop also red. And let's make the color something far away, like blue. That's a nice blue. Okay, so let's take a look at it with the new colors. Okay, so the stops are red and the color is purple. So now, like we said, we're going to change gravity and put it in the x direction to see what happens. Change it to 0 in the z and positive 9.8 in the x. So we'll expect this color to slide forward. And it already slid forward so fast we didn't even have time to see it. So there it's sliding forward in the x direction. Okay. So let's change gravity to what it should be. It should be in the y direction, in the negative y direction. And 0 in the x. Apply and OK. Okay, now let's connect our springs between these two. So we type in spring and damper force. Connect one side here and the other side here. And we said the natural length was 1. Spring stiffness is 100. And we'll sense the force and apply. And we'll do the same for the other side. Oh, okay, wait, I connected it to the center. By accident, I should be connecting it to this right spring. Okay, let's name this right spring. Right spring. And we'll name this one left spring. Left spring. And we'll connect the follower with the left spring and the base with the stop, left spring stop. And they're both at 100. And I think I forgot to mention that we can also use this joint to translate our collar. So let's say we want to translate it 0.25 in the x direction. So now with the spring force, it should go back and forth. So let's have a look at it. Yeah, there, now it's going back and forth due to that initial it starts 0.25 to the right, 0.25 meters, due to that initial displacement of the spring. Okay, now we want to add our pendulum. So we copy this again. And let's look at it from the top view so we can decide. And let's change the color of the pendulum. Let's choose a color we haven't used yet. We'll make it this color. Give OK. And we need a frame at the top of this. Well, let's change the dimensions first. We said that the pendulum is 1 meter long, and I can make it 0.1 and 0.1. 1 meter long. Apply F5. It's 1 meter in the Y direction, not the X. So let's change it. Apply F5. Okay, perfect. Now we need a frame here at the top so we can connect it through a revolute joint to the collar. Okay, so let's delete our existing frames and create a new one. 5. Call it top. Use selected feature and save. Apply F5. And there it is, the top. Close this. And here's our collar. Well, this is our pendulum. Let's rename it. Pendulum. So let's squeeze it in here. I need to move these three up a little bit. Okay, like this. Squeeze our pendulum here. And I'm not going to use this port, so I don't need to see it. We just really need the top. And the top is going to be connected to the R of this one through a revolute joint. So revolute joint. Okay, and if we read up on the revolute joint, it basically has a lot of stuff to say here, but the most important thing is that it's going to rotate around the z-axis. Well, if you rotate around the z-axis, you're providing us what we want. Basically, our theta is going to be in the xy plane if you rotate around the z-axis. So let's connect it just as it is. Top and right. And let's also give this an initial position. Let's say it's at 45 degrees. Apply and OK. I need to set the masses. I forgot to set the mass. What did we say the mass of the collar was? 1000. It's too big. Let's make it 2 kilograms. Apply and OK. And we'll make the mass of the pendulum 1 kilogram. Apply and OK. And now let's run it and see what that looks like. Okay, so that's what the pendulum looks like. Maybe we can make this opaque so we can see more of what's going on. Or is this already opaque? Opacity, let's make it 0.75. Will that help us? Yes. Okay. So there you have it. That's the Simulink setup for a collar with a pendulum coming out of it. And I realized that I need to make that taller, make this 0.2, so the springs are not at an angle. Okay, that's a mistake. Let me fix that. Collar should be 0.2, not 0.1. 0.2, 0.2, and 0.2. Apply, F5, okay, and run it. Okay, there, that looks better. Okay, let's add to our Simulink model some parameters so we know right off the bat by looking at it exactly what the values are. So for instance, the 45 degree here is going to be the theta naught of the pendulum. So I'll right click, properties, block annotation, and then I'll come down here to position or something like that. Position target value. So, and we'll get the position target units, and we'll name it theta underscore 0 equals this. So let's see, how does that look? Okay, so that's our initial position. And this joint here, we used it to define the initial position of the collar, which was 0.25 meters. So just by looking at it, let's pull up that value too. Okay, so we right click, properties, block annotation, and it's probably going to be position target value and position target units, and we'll say x underscore 0 equals this. Apply and okay. So 0.25. So the base plate, we don't really care about it. We just know it's static. The left spring stop is also static. The right spring stop is also static. Let's get the pendulum or the mass from the pendulum and the collar. So let's get the mass here. It's going to be under block annotations, properties, block annotation, mass, and mass units. And we'll say mass of the pendulum. Mass pendulum. Apply. Okay. And we need the mass of the collar too. Right click, properties, block annotation, mass of the collar. Let's say M sub C equals this. Apply and okay. So there's the mass of the collar. Let's move this out of the way. Okay. That's the masses. We got the masses. We got the initial positions. Let's get the spring constants too, so we know what the spring value is. Oh, whoops. Again, properties, block annotation. Let's say spring constant. What is it? Spring stiffness. Called it K. And let's say the natural length too. Let's call it L, and natural length is 1 meter. And natural length 1 meter units is this. And let's add spring stiffness units too. Spring stiffness units in newtons per meter. is here. Apply, okay. And we know that this is a copy of the other spring, but let's just put it here anyways. Properties, natural length, and spring stiffness K, spring stiffness here, the units, apply, and okay. And those, now we showed our parameters and initial conditions in our model. Let's collect some values so so we can show them in the plot. So here we can sense the position, and that'll give us the theta value of the pendulum. So we double click, sensing position and velocity. Let's pick up both of those. Apply and OK. And let's do it for the same for the collar too. Let's do it for the collar. We need it under the prismatic joint to pick up the position and the velocity here. And now we need some scopes and some PS Simulink converter. And we need a scope to plot it. So we're going to need 4 of these now. But let's do one and then copy the rest of them. So this is for the position, like this. And the other one. Okay, I just showed how to connect the Simulink, PS Simulink with a scope, and from the output of the position, that will give you the angular position of the collar. And off the screen recording, I added these 3 to it, which is the angular velocity with a PS Simulink and scope, and position and velocity of the prismatic joint, which is connected to the collar. So it's the collar position and collar velocity. And if you double click the scope of the collar position, it will show you the collar position there. After you finish modeling this collar with sandwiched between 2 springs and a pendulum in Simulink, you were worried that it's not validated or you have no way to verify it. One way to verify it is to derive the equations of motion for Lagrangian and then solve them using ODE 45, because they're going to be a set of 2 ordinary differential equations, and then you can plot and animate your results. So this M file, we're just going to derive the equations. As you can see, we have defined these symbols: symbol of the spring constant, mass of the collar, mass pendulum, G for gravity, length of the pendulum, and these are our generalized coordinates that we have to define when we use Lagrangian method to find the governing equations of motion. So the 2 generalized coordinates for this problem are x and theta. So then we define x dot, and x double dot. So x dot will be velocity, x double dot acceleration. And then theta will be the position of the pendulum. It defines exactly where the pendulum is. And theta dot will be the angular velocity, and theta double dot will be the angular acceleration. So to start with Lagrangian, we know that we need to find the kinetic and potential energies. So let's start with potential since it's easier. We know it'll be the potential energy due to gravity and potential energy in the spring. The potential energy due to gravity will only be made up of the pendulum, since we can take our datum to be at the collar. So the collar will not have any change in potential energy. So it'll be negative mass of the pendulum times gravity times L over 2 times this L over 2 times cos theta. And the potential energy of the spring is 1/2 kx squared. Since there's two of them, it'll just be 2 times 1/2 kx squared. And let's run that to get our potential energy. Okay, there's our symbolic term for potential energy. And now we do the kinetic energy. So the kinetic energy is going to be actually made up of 3 components, as the pendulum has a rotational kinetic energy and a translational kinetic energy. So we'll call it, and the collar just has a translational kinetic energy. So kinetic energy collar translational plus kinetic energy pendulum translational plus kinetic energy of the pendulum rotational. So now let's define these 3 terms. Kinetic energy of the collar is going to be, well, we need to, okay, we have x dot defined, yeah. So it's just x dot 1.5 times the mass times x dot squared. That's easy. Mass of the collar times x dot squared. And now the kinetic energy of the pendulum. Okay, to get the kinetic energy of the pendulum, we need to define the velocity of the center of mass of the pendulum. So that is going to be depend on, we can first find or define the position vector of the center of mass of the pendulum and take the derivative of that. And in order to get a position vector, let's define unit vectors EI and EJ. So these are unit vectors, and they will help us define the position of the center of mass for the pendulum. So we'll call it RP. It's going to equal x plus L over 2 sine theta. That will be for the E, for the I component. I guess I could have just also wrote this as a vector, but okay. And now for the J component, it's going to be L over 2 times cos theta, because the motion of the collar doesn't affect the position in the J direction. So that's our J. Put this here. Okay, now if we differentiate this, we'll get the velocity of the pendulum. So we use our diff function, R sub p, with respect to x. We need to use the chain rule, multiply that by x dot, and then we have another variable that is changing with respect to time, and that's theta. So we need to add it and this with respect to theta times theta dot. So that's the velocity. Now we can get the kinetic energy, translational kinetic energy of the pendulum. It's just going to be 0.5 times the mass of the pendulum times the dot product of the pendulum with itself. Okay. And now the rotational, that was translational kinetic energy. Rotational kinetic energy of a rod has this equation. It is 0.5 times the moment of inertia times theta dot squared, where the moment of inertia is 1/12 times mass of the pendulum times the length of the pendulum squared. So I think that will define the kinetic energy. And then let's simplify it. See what we get for kinetic and potential energy of the system. Let's remove this colon and run it. Okay, I didn't define the color. Okay, hold on. I need to just put an underscore T here. Okay, so those are the terms for the potential and kinetic energies of the system. Next, we will plug those into Lagrangian equations of motion. Okay, so after finding the kinetic and potential energy terms symbolically, we are ready to derive Lagrangian equations of motion. So first we'll do it with respect to the first generalized coordinate, which is x. So we'll take the partial derivative of the kinetic energy with respect to x dot, and that'll simply be derivative of t with respect to x dot, kinetic energy. And then we need the time derivative of the partial derivative, which we just found, with respect to time. So here we need to use the chain rule. So we'll take the derivative of this term, and we'll have to do it first with respect to x, and multiply by the derivative of the inside, and then take it with respect to x dot. And then theta, and then theta dot. The x dot, this will be theta, and then this will be theta dot, and this will be theta double dot. So that's the first term of the Lagrangian. Now we need to find the second term, which is the partial derivative of the kinetic energy with respect to just x by itself. So that's easy to find. It's just the derivative of potential kinetic energy with respect to x. Let's put a space here. And now we do the same for the potential energy. And then equation 1 will be the first term minus the second term plus the third term. Equation 1, we'll call it be this minus this plus this. Let's have a look at that. And there's your first Lagrangian equation of motion with respect to x. And then we'll have to do the same for theta, so we can just copy and paste. So first we change this to from x dot to theta dot. Same here. dp dt p theta d dt. And then this term will come in here. And we'll keep these the same because we're going to have to take the derivative with respect to x dot theta and theta dot, and then multiply by the inside because it's the chain rule. We can change this to ptp theta and ptp theta. And we'll change this to equation 2. And then we'll change this, this, and this. And this is no longer x, it's going to be theta. And that'll be equation 2. Let's see if everything ran smoothly there. Okay, so those are your two equations of motion developed symbolically using Matlab symbolic capabilities. Next, we'll have to solve these two equations using ODE 45 function. Okay, so here are the two equations that we derived, Lagrangian equation 1 and equation 2. This one is for the x generalized coordinate, and this one is for the theta generalized coordinate. And to be able to plug this into ODE 45, we need to have the theta double dot and the x double dot all on one side of the equation. And we see here we have an x double dot and a theta double dot on the left hand side here, and a theta double dot and an x double dot also on the left hand side here in equation 2. So when we put it in matrix form, it comes out to be like this. This is matrix A left multiplied by this column matrix or column vector equals the right hand side. So now to get this column vector to be on the left hand side by itself, we need to multiply the right hand side with the inverse of this matrix, this 2 by 2 matrix. Okay, so here in these few lines of MATLAB code, we just do what we said on the previous slide, where we have A is the 2 by 2 matrix and the right hand side is the column matrix with everything without a theta double dot and an x double dot in it. And then we just take the inverse of A and multiply it with the right hand side to get the left hand side, where the first element of the left hand side is x double dot and the second one is theta double dot. And these are now your Lagrangian equations of motion solved for the second order derivative of the generalized coordinates x and theta. Okay, previously we showed how to come up with x double dot and theta double dot. ODE 45 only solves first order ordinary differential equations, so we have to do a little trick here to reduce the order of the second order ODE to a first order ODE. And when you have x double dot and theta double dot by themselves on the left hand side, it's very easy to do. So you come up with a matrix or a column vector that's z x dot theta theta dot, and then you take the derivative of that column vector to get x dot x double dot theta dot and theta double dot. Well, these two terms we solved for symbolically previously, X dot and theta dot, well, we know from this column vector, they are Z of 2 and Z of 4. Okay, now we're ready to start simulating since we've completed solving for X double dot and theta double dot. So we'll start by clearing the screen, clearing figures, clear all variables, and close all figures since we're going to do some animations. And then we'll set our constants, which are going to be mass of the collar, 2 kilograms, mass of the pendulum, 1 kilogram, spring constant, 100 newtons per meter, G equals 9.81, the length of the pendulum, 1 meter, and we'll set our initial conditions. So we'll push the collar to the right, 0.25 meters, and of course it's going to be no motion in the x direction, so that's going to be 0. It's going to be released from a still point, and theta initial is going to be 45 degrees or pi over 4, and theta dot initial, since it's at rest, is the word I was looking for previously, it's going to be 0. And let's put those all initial values in a row vector just so we can feed them easily into ODE 45. Like this. And there's our row vector. And now we can set an initial time. Let's say 0 seconds. A final time. Let's go out to 20 seconds. And let's set a time span using lint space of T final and T initial. Okay, the next few lines, I just copied them straight in from the symbolic development. As we showed earlier, this is Z of 2 and that's Z of 4. This is X double dot and this is theta double dot. It's a little bit long. And then once you have that, you just plug in directly into ODE 45, and these are your inputs, Z dot, time span, initial values, and it's going to return Z double dot. And then you can just set X dot, theta dot to all the vectors or to each row. And now let's run it. Okay, let's save it. Call it simulation file color spring pendulum. And let's see, edit run, unrecognized function time span. Okay, let's make this capital, F5. And there it ran. So let's see, what does Z look like? That's Z. New code section, and we'll start animating the results that we just simulated from ODE 45. So clear again, clear the screen and clear the figures. I just clear the figures, but we don't want to clear our variables just yet. If we clear the variables, we'll lose all the information. And I have another video showing how to animate a sliding box, so I won't be going into too much detail on how to do that. So, it's just basically using the plot command with the 4 points of the box. So we say for I equals 1 to the length of x and capital X. Now we put in the 4 points of the box at all times, and we just assume that it is a side of point 2. X of I minus 0.5s, X of I plus 0.5 times s, X of I plus 0.5 times s, and X of I minus 0.5 times s, and X of I minus 0.5 times s, and Y is the Y coordinates of the box. So it's a negative 0.5 times s, negative 0.5 times s, positive 0.5 times s, positive 0.5 times s, and a negative 0.5 times s. And we plot x and y values as they will change for each iteration. I'll color it blue, and let's say axis equal axis min max, and hold on statement, and now we can just plot this or run this, simulate this, see what it looks like. Should just be the box going back and forth. Oh, I forgot to get the frame. Let's say f equals get frame for each frame, and then movie of f like that. Why is it doing that? Maybe I need a hold off statement or something. Axis. Oh, okay. I'll need the hold off statement. Min max, min max. Oh, this should be positive 2 like that. Okay, now let's run it. Okay, I need a hold off statement. Hold off statement. I think I need it here. Hold off. I don't even think I need this. Hold on. Now let's see it. Okay. There's the box sliding through the, as per the x values in the simulation. We show now, we showed the box previously sliding back and forth. Now to animate, I put a spring on the right here in this next few lines of code. It shows you the spring on the right. Then this will be the spring on the left. And then we need the pendulum, which is always going to be between x, the position of the box in the x direction, and then the position of x plus L sine theta, that's the x1, x2, and y will always be 0, and it'll be negative L cos theta pointing downward. And I just made it thicker with the thickness of 2 and color red so we can distinguish it from the box. And the springs, I painted them black here with the K. So let's have a look at that. And there's your box being animated. I put a 5-second delay for the first when I equals exactly 1. Okay, and then the final bit of code doesn't really need much explanation. It pretty much explains itself. I just put subplots and plots of the first plot will be time with respect to position. Second one will be time with respect to x dot or velocity. Third one will be time with respect to theta. And the last one will be time with respect to angular velocity. So if we run that, we get this nice figure here, and we compare that with the plots that we received from the Simulink model. Okay, I hope you enjoyed this video and it was a learning experience for you. And if you like it, hit that like and subscribe button. Thanks.